All right, welcome. This is video number 3 in our liquids and solutions unit. So this video is going to be on factors that affect solubility and solubility of gases. And you need your notes open to page 23. Again, this is page 23 in the notes. First up, factors that affect solubility. When we say that, that means how fast does something dissolve? How quickly will something dissolve? What will affect how much of something you can get to dissolve? And there are 3 main factors that affect it, which you might have worked out from the lab. They are stirring temperature and particle size. All 3 of these have an impact, and these are actually the only 3 things that have an impact. If you say, well, if you have more solvent, if you have more or more solute, that's not affecting solubility, because solubility is how much you can get something to dissolve in a set amount. So you're sort of saying per a certain amount. If you notice the solubility chart for in your reference table, that's per 100 grams of water. You can't change that. How much can you get to dissolve? So stirring, what stirring will do is to increase the rate is when you stir, you're constantly bringing fresh solvent into contact with your solute. So it's like you're constantly bringing new water in to dissolve your solute. And if we remember, in the dissolving process, water actually surrounds the solute particles and pulls them away. Remember that surrounding of the sodium and chloride ions. So by constantly bringing in new water, you can get new water to surround the solute and pull it away from the bigger solute particles and get your stuff to dissolve faster. Next up is temperature. Now, higher temperature increases solubility rates usually, and then we're going to be looking at the exception to this here. If it's a solid, then your chances are very, very good that if you heat up your solvent, you can get your solid to dissolve faster. The reason for that actually goes back a little bit to kinetic molecular theory with gases, in that if your solvent particles are moving faster, again, you can dissolve your solute more quickly because they're simply moving around more, and they can essentially pick off and surround the solute particles faster, and you have a faster rate of solution formation. And then lastly, particle size of your solute. The smaller your particle size means more surface area. If you think about a really, really, really big log, one that's really, really thick, that will burn a lot more slowly than if you were to burn kindling. And the reason is the kindling is a smaller particle size. It has a lot more of exposed surface to the flame. A really big thick log, there's all this wood that's in the middle of the log that isn't exposed to the fire. So that wood clearly isn't going to burn because it's simply not exposed. It doesn't have a chance yet. So there's only a small amount of surface area in a really big thick log that's exposed to the flame. So it's not going to burn as quickly, versus kindling that has lots of surface area, very small twigs, etc. They have lots of surface area exposed to the flame. So the smaller your particle size, the more exposed surface area, the faster you can get your solute to dissolve in your solvent. And the example that you might be familiar with is granulated sugar is going to dissolve faster than a sugar cube. That's the idea. Now, factors affecting solubility of gases. See, we said that increasing temperature increases the solubility, and that's true for most solids. Gases, however, do not play by these rules. So 2 things that affect the temperature, the solubility of gases, are temperature and pressure. But temperature, it's going to actually have an opposite effect. If we increase the temperature of a solvent, we increase how much solid we can get to dissolve. But increasing the temperature of your solvent causes gas particles to leave your solution, because your gas particles, they're simply moving so fast. They have so much energy. And if you're increasing the temperature of your solvent, you're giving energy to gas particles that might be trying to dissolve, because you can dissolve a gas in the liquid. You absolutely can. And if they have so much energy, they're simply going to leave the solution. They're not going to stay in their solution. So gas particles are significantly less soluble in liquid at high temperatures. So we have this opposite effect. So whenever we talk about solubility of gases, I like to talk to you about soda, because soda is quite literally a gas that is dissolved in a liquid. That's what gives it its fizz. And then you flavor the liquid however you want it to be flavored, lemon, lime, or cola flavored. But what gives soda its characteristic fizz is gas particles. It's actually carbon dioxide that's dissolved in the liquid. And when is soda at its fizziest? When is there the most fizz in the soda? Well, if there's the most fizz in the most fizz is coming from the most gas that's dissolved in it. So gases or soda is fizziest when it's cold. So that's why we keep soda at cold temperatures. Low temperatures, that's when our gas is most soluble. And the reason is because the gas particles are simply moving more slowly. They don't have enough energy to escape the liquid, right? There, we know that at low temperatures, they have very low average kinetic energy. They don't have enough energy to escape the surface tension of the liquid and leave the solution. So that's why we keep our soda, in our refrigerators and not in our ovens. That's why we don't microwave our soda before we drink it, because keeping it cold keeps the gas dissolved. And this graph is simply showing that at very low temperatures, notice that we have the most, these are all gases, but for all of these particles, you have the most of them dissolved in your liquid at low temps, and as we're increasing the temperature, their solubility is going down. But pressure also affects the solubility of gases. And that's why we keep our soda closed. That's why it comes in these pressurized cans, because pressure impacts it. And our gases are going to be most soluble under high pressure. That's why we say, don't shake up a soda can, because it's already highly pressurized and you're messing with that when you shake it up. And that's also why you hear that fizz, that crack, when you open up a soda can. It's some of the pressure from that very high pressure container escaping as you're opening it. And that's also why, even if you were to have an open soda can and you kept it cold, it would still go flat in the refrigerator, because you have lowered the pressure of the mixture by simply opening it. Air pressure is a lower pressure than the pressure that's inside a soda container. When this diagram right here is showing this idea, and this is actually quite literally showing how we get the fizz in soda. What they do is they would have like the soda liquid, which is here, and then they flood the surface of the liquid, like right above the surface of the liquid, they put a whole bunch of carbon dioxide gas, but it's in this container that has like a piston that can then press down on it. And when the piston presses down, we are increasing pressure, and that forces the carbon dioxide to go into the solution, and now we have a whole bunch more of dissolved gas, and then they simply siphon off this liquid and put it into the cans, and then, boom, there is our carbonated soda beverage. So soda, if you can remember the conditions under which soda is fizziest, you can remember the conditions under which gases are most soluble in liquids. Very low temperatures and very high pressures, to basically try to keep the gas as condensed as possible, to keep it in the solution.